Hello, everyone, and welcome to episode 4 of The Future of Energy, a production of the Denver Museum of Nature and Science and the Institute for Science and Policy. I'm Trent Noss, managing editor at the Institute, and we're happy to see so many of you spending part of your afternoon with us. Thank you. So today, we're going to be focusing on one of the more under-discussed elements of renewable energy, and that's transmission. It's one thing to create energy with wind and solar, but it's quite another thing to get that energy to where people are. And even though we've previously talked in this series about trends in grid decentralization and improvements in any energy storage capacity, there's still no contest about the fact that the most effective way to get power to where people live is through wires, whether that's in the air or in the ground. But as we've seen over the last few decades, as renewables have really expanded, the transmission infrastructure build out has sort of lagged behind. And there's a lot of reasons for that that we'll get into here shortly. And that's just because you can't put transmission wires anywhere. It's very difficult to work through a lot of the siting, a lot of the implementation. High voltage wires can't just spring up overnight. And that is a huge deal as we're staring down some pretty ambitious decarbonization targets here in Colorado and of course more broadly. So just like you can't make a cake that would taste very good without flour, we really can't talk about nationwide renewable implementation without this very important ingredient. So here to discuss all that with us today, we're happy to be joined by Dr. Christopher Clack. He's the founder and CEO of Vibrant Clean Energy LLC, which he founded in 2015 to pursue more intelligent electric power system design here in the US and abroad. Dr. Clack hails from the UK, where he studied mathematics and statistics at the University of Manchester, and then went on to study applied math and plasma physics at the University of Sheffield. And since 2010, he has worked at the intersection of math, science, and policy. And he actually started off investigating sunspots, which can inform predictions of solar storms that can interfere with GPS and power systems here on Earth. He went on to lead research efforts at NOAA, where he created the National Energy with Weather System, or the NEWS simulator, and then went on to the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder. And in early 2016, Dr. Clack was a co-lead author on a pretty groundbreaking paper in the journal Nature Climate Change, using some of his modeling to show how the US could use nationwide transmission grids to reduce carbon emissions by 80% by 2030, and do so without raising the cost of electricity and without increasing our energy storage capabilities from really where they are today. So we're delighted to have him here today. Chris, thanks for joining us.
Thanks, Trent. Great to be here. I'm just going to share my screen to make sure people can see the slides.
Terrific.
Yeah. So Trent's done a great job of introducing me, so I won't bore everyone else's time on talking about myself. But what I'm going to try and talk about today is kind of level set what transmission is and the way that I think of it. Talk about why you may have started to hear more about it lately than maybe previously, and then show some results of what we see the benefits of large-scale transmission in the US, and hopefully some of the pitfalls that might make it harder or easier to get it built. So from a really kind of simplistic mindset, transmission is just the movement of energy, or electricity in this case, from where it's generated to where it's being consumed. Where it gets tricky and complicated is we've built a super connected, what we would call transmission network, where we have lots of generators and lots of consumers, homes, businesses, industry, and electrons don't move where you want them to. You can give them an impulse or a force and they will go along the path of least resistance, as we call it. And so they do some funny things. And so we've had to build this very complicated system to deal with two things. One is the alternating current of electricity, which is basically a consequence of how we produce the electricity. And then we've had to do something to be able to move it a long way. And that's put it up to very, very high voltages. And we put it up to very, very high voltages because we want very small currents, because that's how we get heating in transmission lines. If you ever feel the back of a wire that's very hot, it's because you've got a low voltage and you're drawing a lot of power, which means you've got a very high current. And that's what will heat it up, start fires and cause problems. And so for our transmission system, we have very, very high voltages of the range of 200 to 500,000 volts. And then by the time it comes into your homes, it's around 240 volts to 120 volts, 110 volts, depending on whether you've got a single phase or a triple phase. And then because this is so complicated, we've kind of decided to break the system down into multiple parts. And so we have what we call the transmission grid and then the distribution grid. The distribution grid was originally built purely to absorb power and put it to the homes from the transmission grid. And the transmission grid was really to move electricity about from coal plants, nuclear plants, natural gas plants, hydro plants that were really far away from the load. And so on these images that I've got on the screen, on the left is kind of a schematic of the transmission and distribution grid. And on the right, we're showing a little bit of detail on the fact that to get between these different phases of the transmission and distribution grid, we need things called substations, transformers, and all they do is change the voltage and realign what we call the phase of the electricity. And that's because as things travel, waves as they travel will sort of communicate with each other and they'll change shapes. And so the engineers have very smartly put lots of these transformers and substations to correct for all that on the transmission system and in the distribution system. And all these different voltages mean that they all have to communicate with each other and send power with each other in a very organized way. And so we've come up with lots of ways to do this. But we found a new technology quite a long time ago now. In fact, when electricity started, they started trying to build these. These are called DC lines. There's a few of them that exist today. And what we'll show towards the end, I think, is that HVDC is probably going to be the next revolution in transmission build out, in my opinion. And the thing that I like about transmission from a personal standpoint is that everybody listening today and everybody that's working, everybody is connected by a wire. You can trace a wire from your home or your office to anybody else in the continental United States without leaving the system. And so you can imagine how big and complicated that is. And so it causes tremendous difficulties. But without that system, we wouldn't be able to have the modern society we have in the US today, or anywhere, in fact. So what does that look like in the US? So I've drawn this simple map from work that we do at VCE. The blue lines here are transmission lines that are higher than 138,000 volts. And the dots represent the power plants that exist today, or existed in 2018 more precisely. And hopefully you can see the state borders that exist as well. And you can see that the western half of the United States has much fewer lines than the eastern half. And that is because a lot more population live in the eastern half. But what you'll notice is none of these lines are very straight. And that will come to one of our difficulties of transmission, is that it's very difficult to cite these things, which we may get to in the questions. But essentially, these paths are never going to be straight lines. When we model this, we will model it all with straight lines, but we know that it's never going to go in straight lines. There's barriers, there's physical barriers, mountains, rivers, people owning land, but also there's difficulties of just needing the electricity to flow in certain ways. The different colored dots represent different technologies. Hopefully all the rest of the plots in my talk will have the same colors so that we won't have to go through it each time. But the big ones to note is black is coal, gray is natural gas, purple is nuclear, light blue is hydroelectric, green is onshore wind, red is solar. There's a dark red and a light red. And then there's some browns and some yellows, which is CCS and storage. And I'll talk about CCS and other technologies as we get further into the talk. But essentially, this is probably one of the most complicated machines that humans have ever created. And what we need to do in the United States in the next 35 years, and we have to replicate this on every country in the world, is completely transform this entire system. And we've got to do that in less than ideally less than 20 years, but likely in less than 30 years, which sounds like a long time, but as we go through this, we'll see hopefully that it is not as long as people might think. And for the older ones among us, we're actually closer now to 2050 than we are to 2030. Closer to 2050 than we are to 1990, beginning of 1990. So, which is, it's depressing for some of us, but for the younger ones, not so much. So why is transmission coming up so much? Well, the reason we hear a lot about it in some areas is because it's so difficult, but the reason that it's being fought for is because it makes a lot of things easier. The first thing it makes easier is decarbonizing the grid, and I will come into why in a second. The second is it makes it more efficient to electrify other sectors. If anyone owns an electric vehicle or has an electric cooktop or has decided to get a heat pump or a heat pump water heater or an electric water heater, all those things draw more and more power to places that we didn't used to have them. And if we have transmission, it means that we can do this more easily, and we invest in it. We'll make it more easy for more people to get access. It also allows people to put more rooftop solar on their homes. The second thing it does is it reduces electricity costs. And this is kind of tied to our last point here, which is that there's interstate markets for electricity. Where wind and solar exist is not typically where people live, which I will go into. But more importantly, the way the grid has been set up is we have things called balancing areas where generation and supply needs to be matched. And they tend to be quite small based on the fact that when they were first founded, electricity providers were close to where the customers were. But now we can move further and further away because of transmission. And when we do that, it means we can go to better resources. If you're from Wyoming, you can be close to a coal plant, but they also have lots of wind. If you're in Texas, you can go near some gas. And so it makes things a bit easier. And then we can buy those products for cheap versus doing it all locally and having it shipped in. The other things we can do is reduce curtailment of renewables because we can share with our neighbors rather than doing it on our own. And then one of the ones that we found a little heretical when we've studied it, but we have shown it several times now, is that with transmission, we actually increase storage, electric storage, and DER integration, which is the inverse of what most people might think. Storage and DERs, everyone thinks that might be local and not need transmission, but what we found actually is they actually pair very nicely with transmission, and they actually increase and they reinforce each other. And that comes down to the technical details of planning a grid above the sort of the first level discussion of how would you, provide enough power. So I'm not just talking about my own opinions here. This is studies that have been done time and time again. And more will come out. With just one today came out from Princeton showing we need transmission. Yesterday, I believe a study came out from MIT that showed transmission regionalization works. We have the NREL refs here, which is 2012, which showed that we need new transmission. A paper that I worked on in 2016 was the first in the US to show continental US with wind and solar to get over to 80% by 2030. We had the NREL ERGIS study, which is the Eastern Renewable Grid Integration Study. And that looked at just the Eastern Interconnect, but at high detail. That also showed huge benefits to transmission. We have the SEAM study, which has finally been released by NREL. That was around 2018 was when most of the work was completed. That showed what we call a macro grid, helped. ASIG, which is the American Coalition for a Grid, we looked for them on an Eastern study again and found again, similar to ERGIS, that you can get to high penetrations of renewables. We actually got up to 95% renewables in that study. And there's a study coming out from us in January 2021 before the new administration, which will look again at a national HVDC grid in high resolution, which we'll give some insights to at the end of this. And what all these studies kept showing, and the recent studies have reinforced this, is for every dollar you spend in transmission, you will probably get between $2 to $7 back in the economy somehow, either reduction in electricity or energy costs, improved jobs, or pollution mitigation factors as well. And what we showed in the 2016 paper, and others have shown since, is actually that the transmission system enables any resources to go on the grid in a fair manner. But because wind and solar are so cheap now, as we'll show, we actually see the largest benefits because of access to renewables. And hopefully I'll go into that. So why do I keep going on about the grid and transmission in particular being helpful for renewables? Why does that matter? Why don't I talk about helping coal or gas? And so my bias is that I would like no more CO2 from fossil fuels going into the atmosphere. But as a scientist, I look at this from what's the lowest cost option, and then see what the externalities are, as we call them. But what actually happened is, from when I started studying this back in 2014, pretty much wind and solar are the cheapest thing you can put on the grid. If we look at the chart here on the right side from Lazard, 2017 was the time when we were certain that wind and solar were cheapest, and we're now in 2020, and they're now even cheaper than they were. And when I started, wind was, but solar wasn't. And so these costs have come down dramatically, and now we're seeing them integrated. And the problem with wind and solar, or the difficulty with wind and solar, is that they're variable. And so we need to solve that problem. And so to solve that problem, we have to think big. And so this comes back to my thinking when I was studying the sun, which is, if you look at things from really far away, everything looks really smooth. No matter how big or how bumpy something is, if you go far enough away, it looks smooth. And when you look at the Earth and the atmospheric system, what you find is that it's very uniform in terms of the energy distribution and how it gets moved around the planet. And primarily everything is driven by the Earth, sun distance, and how much the sun is outputting. And the sun output does change, but not by a huge amount. The Earth sun distance does change by more, but that variability at a planetary scale then ends up being around 5 to 8% oscillation. But if you live anywhere in the United States, or anywhere in the world for that matter, some days it'll be hot, some days it'll be cold relative to your location. It might rain, it might snow, it might be windy, it might be cloudy, but all these things will happen, and people will think that it's chaotic and noisy. But in fact, if you look at a large enough scale, all these things come together. And I can show this in a simple graph that basically all we did was we just looked at the world, and we looked at different patches of that world and how variable the weather was. And this particular one is for wind. And so what we did is we just plotted it and see what happens as you go to larger and larger scales. I will note the x-axis here is a logarithmic scale because weather acts at logarithmic and exponential scales, and so that's why we have that. But essentially, as you go to larger scales, the variability drops. It'll never go to zero because there's always things going on. But if you go to larger and larger areas, your variability will drop. And so I've marked a few places on here: Maryland, which is quite small; Colorado, which is reasonably big; Texas, which most people agree is fairly large; and then the continental United States, huge. And continental United States has variability of less than half of what Colorado will see when you go to the CONUS level. And so if you can tap into that, what it means is you can access wind and solar that isn't correlated to your production or your needs. And I'm going to show that in two final graphs. There's only one more graph after this, I promise. And what these graphs are showing, the one on the left is a bit more complicated. The one on the left is what's called a frequency density of energy. And all you need to really think about for this is, when there's a spike, it means there's more energy available at that time period. And so I've just numbered them there. When you look at the wind power, you find that on a daily scale, there's 4 time periods where there's more energy available. And that's at a single site. And then there's like a flat piece, which means that the energy is basically constant across that. And that's a good thing. What that means is that if you move away from that site, the correlation should drop off exponentially. And so on the right-hand side, what you're seeing is a correlation from one site to other sites in the United States. And then all we did was just move those sites apart from each other. And you'll see that it starts off perfectly correlated. Obviously, if it's the same site, it should be. By the time you get to 1,000 kilometers away, you've almost minimized the correlation. And if you go really, really far, your correlation will go back up again because you'll come round the planet back to where you started. And so what we find is basically 1,200 kilometers away, you get very low correlation. And that's actually called the Rossby radius of deformation, for those that are interested in learning about these sort of things. And that is just physically baked into the atmosphere. There's nothing we can do to really change that. And that is just driven by the physics of the solar radiance that's hitting the Earth, the amount of water that's on Earth, and the amount of land mass, and then the speed at which we're rotating sets these in motion. So what it means is if you go outside that 12,000 kilometer bubble, the weather will likely be very different. And typically you don't have to travel that far. But what that means is you need transmission. And so what I'm showing here is a map of the United States at night, at dark. And I've pointed out where Denver is in case it's difficult to find when you're looking at it on a screen. But hopefully what you'll see is that now you'll see why there's so many transmission lines in the plot I showed earlier. The eastern United States has much more population, much more dense urban areas than the western half of the United States. But they're about half the size each, roughly, in terms of area. And so this is where we get the second difficulty with renewables. Where you need most of the electricity or energy, you have the least available space and willingness to build next to communities. Okay, and so we have offshore wind, of course, on the East Coast that we could build, but that's more expensive. But we have lots of resource in the East and Central Plains, but not as many people. But we do have agriculture and other land uses that need to be accounted for. Just as a side note, if you look up towards North Dakota, you'll see lots of little lights, and that's natural gas flaring, for drilling for natural gas, if anyone's interested in natural gas. And so the renewables have siting issues themselves as well as transmission. But the transmission can help those renewable siting issues because we can move the energy from one place to another to tap into this atmospheric battery. What we sometimes forget, or I sometimes forget when I'm thinking about it, is every form of energy that we use is essentially solar energy stored somehow. Oil, gas is just condensed solar energy. Uranium is just explosive energy from a supernovae. Wind and solar as solar energy directly farming of that energy. So let's look at the United States from a different perspective. So we've seen the population density. Now let's look at where the fuel lives for wind and solar. So this is a map of the United States with the capacity factor of wind, and that just means the amount of energy you can get from a site per year as a percentage of what is theoretically possible if it ran at 100% all year long. And so these colors, the higher the number, the redder the color, rainbow color. So I apologize for colorblind or others who find this a bit difficult. I'm sorry about that. But what you'll see here is that the wind is very concentrated in one region. And again, I've put on Denver here just to kind of orientate everyone. And we find that wind lives here. And I just want to take 1 second or 1 minute rather to kind of understand that a little bit. If you look at that triangle, the reason the wind sits there is because there's a mountain range to the right-hand side of it and there's a mountain range to the left-hand side of it. And atmospherically, all the energy gets funneled down that triangle. The wind blows down there typically. And so there's two things with that. One is it means that there's very correlated. And the second thing is that it's very strong because there's lots of plains there. There's not many trees in general. And so that means that we're constrained where our wind is. Okay, there are other sites that we could build in, but this is where we're going to be building a lot of the wind and solar that we need in a lot of the wind of the United States. If we switch to solar, we see a different map. What we see this time is the solar is actually concentrated into the southwest and the southeast. And again, the reason for this is particularly the southwest is obviously we're a lower latitude, but also it's at higher elevation, which is why we get the desert regions. The southeast is not as strong because it's at lower elevation, but also there's a lot more humidity in the air, which means that there's a lot more cloud formation happening. But we do see a lot of solar down there. And what you'll notice is those regions kind of are semi mutually exclusive. There are some overlaps on the western side, but essentially they are in different regions of the United States. Moreover, the solar resource is mostly away from where the population live, and the wind is too. And that really is a direct correlation of people don't want to live where it's blisteringly hot or very, very windy all the time. That just is how it has happened. And so now if we connect that with some sort of transmission network, like this proposed network for an HVDC system, you can move those electrons from where they're created, or the source, to where they're needed at any time step. And we do this in such a way as a network so there's no single fault possible on this system. So the thing that comes out of this is that transmission is needed for several reasons. One is to move electrons around efficiently. We need that anyway, even if we don't care about cleaning the environment. The next is we actually need longer lines, higher voltage lines to move more power more efficiently. And the advent of renewables being very, very cheap means that our source of electricity is two things. One, variable by nature, and two, away from where we live, typically. And so those two things combined mean that we need a new infrastructure build of transmission to move that energy where it's created to where it's now being delivered. And so what I'm going to do now for the last 5 minutes or so is talk about results from a study that's going to come out in January that looks at zero emissions for the whole economy by 2050. So it's a 0 by 50 study that we are doing at Vibrant Clean Energy to look at how do we get the whole economy for the United States to be zero carbon by 2050. Why study it? Why care? Well, I always show this plot. I've been doing this since I was at NOAA. And the reason I show this plot is the yellow line here is the actual additional CO2 that humans have put in the atmosphere since I think since 1800s. And the dotted lines here that come off it are the projected future amounts using them as trend lines. And so what I did was I put the Paris Accord time to start the trend line and then back to 1960 to start the trend line. And so what we found is that the sum total of all human endeavor to reduce emissions has moved the needle of doubling CO2 by 4 years to date. And so what that means is it's going to get harder and harder as we move further forward, but also things have to happen faster. And this is good that it's moving because for the first 5 years of me showing this, it didn't move at all. But now it is moving in the right direction. But each year that we add to the atmosphere, the more stringent we have to be on our emission controls. So this is what the system will look like by the end of this year, approximately. Lots more wind and solar going in this year. I think we're going to have a record amount of wind going in this year and solar. Solar is going to surpass 100 gigawatts this year. Wind will probably get to around 110 gigawatts, maybe more, which is fantastic news. And we're having record retirements of coal plants, another generation. The not so good news is nuclear is retiring quicker than we would like, particularly if we want to abate carbon. And natural gas is still on the rise in general. If we have these emission controls coming in, by 2035, we should see a lot more solar and wind and a lot less coal. In fact, there should be only coal in a few mid-states. And that's primarily because of reliability, but it's also because of the younger plants that can last a bit longer and are a bit more efficient. By 2050 now, we are working on an economy that is primarily wind and solar based. There is storage throughout the country, both distributed and utility. There's distributed solar on roughly 25% of all buildings that exist in the United States, being able to power 25% of our current electricity load. The problem is by 2050, because we've electrified, the load is actually doubled. So we're actually looking at around 10% of the future load. And what this means is we're actually going to be building a lot of things. And what I'm showing here is on the left, the capacity without HVDC, and on the right with HVDC, and that's that super grid that I was talking about. On the left, what we find is that we have to build an additional 500 gigawatts of capacity. And for reference, that's 50% of what exists on the grid today. So we have to build that extra if we don't build this HVDC system. And it's expensive to do that. On the right-hand side, we're showing what we build without it. And what we show is we can build less capacity if we invest in transmission. And that's because we're not going to waste as much electricity. But both these show we're going to be building a lot more wind and solar across the United States by 2050. What does it look like for generation? Well, if we look at it, they don't look hugely different by 2050. What we will notice is that the nuclear share in the HVDC, traditional nuclear is higher, and these novel technologies is lower. For me, that's a good thing because it means that we don't need to invent something that isn't necessarily available, or don't need to have much of this new thing, this miracle cure coming along. Wind and solar can do more. And as these cost curves come down, as we predict future cost curves, of course, these numbers can change. This isn't going to be the final mix, but the trends are consistent across all the price sensitivities that we've done. If you build the transmission, you can build more wind and solar, less other technologies, less storage, and you'll use that more efficiently as well. If we look at emissions, this is for the electricity sector. We're showing a bunch of different emissions here. But what I want to note is by 2035, it's 60% lower for CO2 for the electricity system, but it's 50% lower for the economy. So we've reduced the annual output of the US by 2.5 gigatons by 2035. And then by 2050, we've reduced the full 5 gigatons to 0. This is fairly aggressive in my opinion. If we accelerated electricity decarbonization, we actually find that costs can go up because we're front loading and we're making electrification harder. I won't go into it in too much detail now, but that might be a question for later as to why that happens. But we've seen it happen a few times in our modeling. So how much does this all cost, right? We've got to build stuff. The US is really good at building stuff when it needs to. Well, what we found was there's around $350 billion we'd have to spend on HVDC and the supporting infrastructure. I haven't gone into the weeds of the supporting infrastructure, but basically you can't just build a HVDC transmission line into an AC grid and then just expect it to work. You have to reinforce that AC system. So it's around $350 billion between now and 2030 is roughly the build out time that we estimate. So we've got about 9 years, which is very, very quick. By 2035 to 2040, we will probably have repaid that amount back in savings. And then by 2050, we're looking at $1 trillion in savings. The other way that we look at it, and this is how we look at it here, if we didn't build it, the build out of the system would be an additional $1 trillion by 2050 in spending. And the US can do a lot with $1 trillion. And so we're basically just saying and showing with the study that by building an HVDC, even though it costs us money, the net benefit is so huge that we really should do it, because the other way to look at it, in my opinion, is that the transmission system, if we don't do it, we may not build this system because it'll just become too expensive. What I'm going to show here is this is a huge amount of transmission build out. Of course, there's going to be huge fights to have about where to site it. Shall we go underground? How much extra does it cost to go underground? How do we make sure it's reliable, robust, and resilient to attacks? They're all things that would definitely need to be figured out as well. And then finally, I'm just going to show like what the system kind of looks like in 2050 from a generation standpoint. So this is day by day for a 2050 zero emission economy. Above the line is generation, below the line is charging and losses. And what you'll see is there's a myriad of different technologies that are coming together to fulfill the load. We don't need base load as such, but there is nuclear here that's helping, and hydro and geothermal. But over 80% is from renewables going forward. And then we have to do lots of analysis for our systems about what's the most difficult time to fill. And we found this time here, and we can see it there on the left-hand side, where we're using a lot of storage and nuclear to fill the gap for low generation times. And this is just the least cost system that we've built here. There are other systems that can be built too. So the final thing I want to show, and I'm going to let it run just for a minute or so, is this is the system operating for a system in 2050 for a few days. What the colors are here is the color is the maximum value for each county of what's going on. So if it's any color other than a browny yellow, it's producing more than it needs and it's exporting it to its neighbors. If it's brown, then it's importing power. And so you can see there's a lot of sharing going on. And then these blue lines are showing what the interstate transmission is doing to help your more distant neighbors going on. And we're including Canada and Mexico here. And hopefully what you'll be able to see is the wind and solar, the blues, the greens and the reds, they're much more variable than the browns and the blues as well, which is hydroelectric. And then the bar chart in the bottom right is kind of showing that as an aggregate over the whole United States. And so the reason I'm showing this is two things. It's a very dynamic machine that's going on. But if you zoom out on the right-hand side there in that bar chart, it looks much smoother than everything going on. And so that is why we always model these sort of things in very high resolution detail, because we need to know what's going on at the small scale so that we can back out what's going on in the large scale. So I'll stop there and hopefully take some of your questions, and thank you for your time.
Well, thank you, Chris. That was excellent and full of great information. We are getting a lot of great questions in the chat, so I'm going to try to work through some of those here. A few around the idea of resiliency, and if we were to do transmission build out in wildfire prone areas, for example, someone mentioned the polar vortex, some of these extreme weather events that have been in the news. How would a system be able to work around those type of events so that we aren't seeing the kind of blackouts that California had, for example, this summer?
Yeah, so thank you for bringing up the California one. So the California one was not to do with renewable electricity, or in fact, as much to do with transmission as it was for natural gas. So that aside, but there's still a true point of, as we build these systems out, that should be one of the constraints that we have. And so in our system that we model, we're always looking at, do we need to go underground to protect it? That's the first thing. We can build these HVDC systems underground much more easily than we can AC lines. And that protects you from basically everything, right? It protects you from attack from enemies. It protects you from the weather elements. It protects you from people shooting transmission lines. It protects you from all sorts of difficulties that can be had. But you can't see it, so that makes it a bit difficult for maintenance. But you shouldn't need to do as much maintenance. So that's always part of the plan. But we've become adept at looking after the electricity transmission system to do it. So whenever you have blackouts, it's typically because a big generator like a coal plant, a nuclear plant, or multiple have gone offline to date. It's very rarely because a transmission line has gone down. We're very good at monitoring them. And when they are difficult, then undergrounding them would make economic and prudent sense for resilience.
Mm-hmm. Absolutely. Well, and that gets at another theme we've had in the questions, which is that, are there other alternatives to just the wires and the towers that we're used to seeing in our streets? Those are the most visible pieces of transmission infrastructure. Are there other options, some that are maybe a little more futuristic? Could we run electricity along rail lines, for example?
Yeah, we proposed this back in 2016, and many are working on it and thinking about it. We could really do a lot undergrounding them. Once we underground them, we can run them along interstate highways, or we could run them along railroads. There are a few concerns with that, because if you're an enemy and you know that your adversary is putting all their electricity, all their communications, and all their transport along one line or one route, you would probably target that. But in general, there are alternatives. There are alternatives of using space as a medium. That's a bit more futuristic. We would beam power up to space and then beam it back down. That could work. We don't know whether the losses are worthwhile for that, but that is another way around it. And that would be hyper long distance, right? You could foresee solar being placed in perfect locations and then beaming that energy to space and then back down. But that's more of a sci-fi thing at the moment rather than something that we could be building tomorrow.
Yeah, absolutely. So then when it comes to some of the challenges around siting, are we, there's certainly a collective action problem at work in the sense that it's difficult to get the cooperation necessary to build lines across long distances. But do you see a potential first actor benefit for a state like Colorado or a group of states in a particular region that really just decided, we don't care what the rest of the country's going to do, we're going to get on board and jump into the pool first?
Yeah, I mean, the West would be a great location. Colorado could help with that, to build a Western RTO type structure with an HVDC backbone. There would have to be a lot of undergrounding. Obviously, we've got mountains to cross from Colorado, but that would be very good. Any of the RTOs would be very, very good as well for doing this sort of thing. They have the whole reason to do it of being an RTO, which is a regional transmission organization, is to build transmission and operate the system. And so a place like MISO or an SPP or a PJM, doing that there would be the best way to do it. But the real thing is that you want to have as big an area as possible. So in the US, we have 3 interconnects, and that's how we should start. Those interconnects should be unified by an HVDC grid.
You're certainly on the modeling side and putting forward the data that utilities could use, policymakers could use. How do you see that interplay going forward with, does the action need to come first from the private sector and then the policy catches up? Should we be thinking big picture policy? What's your view on that?
So it's probably both, right? There are private companies that are doing it. We've got this thing called the Sioux Green Line, which is being built between Iowa and Chicago. There's another few lines that are being built. Clean Line Partners tried to do a few things, but unfortunately they collapsed. And the problem with doing it piecemeal is a lot of those are posited on, we need to move power from A to B. China's done a lot of this. They move power from one place to another place. And what that ended up doing was that they had to break up their grid because they made it unstable by doing that. What we're proposing is a network. And so to do a network, we need a federal sort of at least backstop to say, this is what we need to do. This is the plan. Then the private sector and the states can work out how exactly to do that plan. But there needs to be a plan, a blueprint, if you will, to say, right, we need to do this. Now go and figure out the cheapest and best way to do that the engineers and the states and the policymakers and the regulators can all get behind.
Mm-hmm. I'm sure a lot of our viewers probably perked up when you mentioned that this could eventually bring electricity bills down, and that the cost of $1 in will be repaid in these other ways. Do you think there's a way that science can be part of that education effort? Is it a matter of making these facts and figures more accessible? What's the communication arm of this type of research, do you think?
Yeah, it's the realization it's dispelling the myths. There's lots of myths that come along, which is, well, if we just build transmission, it's going to raise rates for the people that have cheap rates now, and we're just going to pay the East Coasters and the West Coasters to have cheap electricity. And what we find is not true. You can sell at a premium from those what we call supply regions, and they will actually get a credit to their bill, and that would have to be decided by the PUCs of those regions of how much credit will go onto the bills. But long story short is the message just needs to keep being repeated and showing, and the studies need to keep happening to show that this is a robust thing. You build more transmission, it lowers the cost. And so, and that's for a myriad of costs of transmission as well. That's even with undergrounding it everywhere if we had to. So the cost pays back. The difficulty then is convincing the utilities and others to that they're going to basically have less money. And so it's good for customers. It's not always so great for the utilities who can charge a premium and get away with it.
Very good. Well, we're coming up on our time here, and I want to thank our audience for all the great questions. Chris, I'm going to get you out of here on this one. Over the next couple of years, you've got a lot of projects that you're working on, a lot of ongoing research. What's something that you can maybe share with us that you're particularly excited about, optimistic about, already looking forward to here in the next couple of years?
I'm looking forward to seeing, there's quite a few studies coming out, but I'm looking forward to seeing in the first 100 days of the new administration what correction will be happening in the climate needs for the country. And I'm particularly interested in how that ties in with the science that's happened over the last 4 years or so that's maybe not been as publicized, but has been working regardless nonetheless with the Congress on their climate action plan and other areas where electrification is now something. When the last 4 years, if you go 4 years back, electrification wasn't really talked about. Now it's all everybody can talk about because we have the technology for electric vehicles, heat pumps. I really want someone to start a company up, the Teslas of heat pumps is what I call it, which is making heating your home sexy again, or whatever the cool slogan needs to be to get people to be interested in that, because that can also lower people's energy bills. Their electricity bill will go up, but their energy bill will go up. And so I'm excited to see more people transition that way.
Well, we'll look forward to seeing how it all plays out, and we'll have to have you back for another conversation at some point down the road. Thank you so much for joining us. This has been a ton of fun, and I know I learned a lot, and hopefully our audience has enjoyed the conversation just as much.
Thank you very much. Appreciate it.
Yeah, well, and I want to thank our entire team at the Institute for Science and Policy, our colleagues at the Denver Museum of Nature and Science who make this program possible. Thank you for all the hard work that you do. And thank you to our audience for tuning in, for all your great questions. I apologize, as usual, we can never get to all of them. Please feel free to follow up with us after the fact. You can email the Institute. You can find us on Facebook, on Twitter, on YouTube. A recording of this session will be available on YouTube in about 24 hours in case you want to share it with a friend or want to revisit anything that you heard here today. And I believe that the slides from today's presentation will be made available on the Vibrant Clean Energy website. So look out for those if you wanted to dig through anything in greater detail. Our next session is going to be on Tuesday, January 19th. That's the day after Martin Luther King Day. We're going to be talking about energy accessibility in Colorado. So I hope you'll join us again for that session. It's going to be a fun continuation to this series. So thanks for spending part of your afternoon with us today, and we'll look forward to seeing you next time.